Very good afternoon. This is Lei WEI from Nanyang Technological University in Singapore. And firstly, I would like to thank the conference committee for the invitation. And it is indeed my great pleasure to share our recent research progress regarding the thermally drawn advanced functional fibers for the wearable electronics. And hope we will be able to have the on-site discussion and very soon. So regarding this topic, and firstly, let's look at in order to achieve, for example, the different functionality and what are the factors that we should consider. So here I listed like two common items in our daily lives. And on the left-hand side, this is a piece of t-shirts. While on the right-hand side, this is a smartwatch. And when we look at the functionality of those two items, and the t-shirt actually can only offer very simple functionality, for example, to cover the human body. Well, for the smartwatch, basically, it can measure all the biomedical signals and to record those signals and to do the analysis. And more importantly, it can also enable like different communication functionalities. So obviously, this smartwatch offers a much wider range of functionalities. So if we look at the materials that to make those two items, basically for the t-shirt, it's almost 100% polyester. Well, if we look at the smartwatch, the materials basically can cover 2/3 of the periodic table. So in order to achieve the functionality, the first factor is materials. So can we use like a wide range of functional materials to achieve diverse functionality? So this is the first factor. When we have this smartwatch and we wear it like every day, and this one can give us, can allocate like different biomedical related data. However, when we use it, and it can only cover a small part of the human body. And if we want to cover basically the full human body, and then the most straightforward way is to wear as many as possible. But in this case, and it's not a pleasant usage case, because here are so many devices, and each of them have their individual interface. And in this case, the second factor that we need to consider is the form factor. So basically, in which kind of platform that we can use to carry those devices. And the next, after we confirm the form factor, the final factor that we need to consider is about the wearability. So in this case, for example, if this kind of a platform can offer us, for example, the long-term comfortable to wear it. So this is the three form factors that we need to consider. And by far, and a lot of platforms have been demonstrated to carry those devices and to achieve the flexible electronics. But in our case, and actually what we target is fibers. And the fibers have been used by humans for over 1,000 years, and it has been a necessary part in our daily life. And for the fibers, and actually for the fibers, they have remained unchanged also over 1,000 years, and to only offer very simple functionality. And to enable different functionalities in the fiber platform, and there have been like many technologies, for example, through the wet spinning, the electro spinning, the melt spinning, the deep coating, and the different types of deposition technologies. And our contribution in this field is based on the thermal drawing process. So for the thermal drawing process, and this is the one that we demonstrated. For example, this is our unique technology, and we can use this type of thermal drawing technology and to achieve the large scale fabrication. And when we look at the thermal drawing here, basically this process starts from assemble this so-called macroscopic preform. So we put all the functional materials, namely, for example, semiconductors, metals in this macroscopic preform, and load that into this drawing furnace, and also thermally stretch this preform into a thin fiber with the extended length. So for example, if the dimension of this fiber is reduced by a factor of 100, and the length of the fiber will be extended by a factor of 10,000. So in this case, and for example, if we have like a 1 meter long preform, this one can easily give us like a 10 kilometer long fiber. And as I mentioned, in the preform level, and we put a lot of functional materials there and semiconductors and metals in a predefined geometries. Then after we fabricate the fiber, and the fibers are device. And in this case, and for example, here I show the cross section of one representative fiber structure. And right in the center, this is a semiconductor core and surrounded by those 4 metal electrodes and further cladded by this insulating layer. And the beauty of this drawing process is that we can encapsulate the functional materials and the structures right inside this fiber. So the insulating material will behave like a coating and to protect the functional parts. And this fiber behaves like a photodetector. So for example, when we shine the light from the through the outer jacket, and the conductivity of the semiconductor changes. Therefore, by reconstruct the electrical signal that read out from those 4 electrodes, and we'll be able to detect not only the intensity, but also the incident angle of the light. And the functionality of the device is not limited to a single fiber, but also further expanded to 2-dimensional, 3-dimensional fabrics. And by knitting those functional fibers together with the common fibers that we use in our daily outfit, and we can form those wearable multifunctional fabrics. So by far, and this technology has been developed over 20 years, and since the first demonstration in early 2000. And we have achieved a lot of functionalities, and for example, in the early stage for the light transition, then gradually move to the surface emitting laser, and for the thermal detection, optical detection, and acoustic detection. The functionality of this fiber is not limited to the fiber itself, but also we also studied, for example, the different physical phenomena inside the fiber. And for example, the fluidic instability and the geometric instability here. And we can also use this fiber to interface with the neural network. And recently, and to demonstrate that we can use this one and to form this kind of in-fiber package, and then to form to encapsulate like the chips into the fiber. So those are the demonstrated results. And however, and there's one major limitation is the material selection for this process. So if we look at the fabrication technology here, and we need to assemble all the solid materials in the preform, and thermally stretch that into the thin fiber. So all the materials that we encapture inside the preform will go through different phase transitions. For example, from the solid to the liquid, and further to the solid phase. And those phase transitions and further limit the material selections. So my group focuses on expanding the material families and try to enlarge the materials that can be compatible with this type of fabrication technology, and to achieve diverse functionality and for different applications. So in this talk, basically, I'm going to focus on our recent results regarding how we can integrate a wide range of materials into this type of platform. So the first demonstration here, and I would like to focus on those brittle materials, and to be more precise, and those are the inorganic semiconductors. So the inorganic semiconductors have been the core of the modern microelectronics, and they offer very high performance and compatible with the CMOS fabrication technology. However, when we use them for the wearable electronics, basically it's pretty challenging, and because they are brittle and they are very rigid. And so in this case, and we try to use the fiber platform and to carry those materials. And within this session, I'm going to share like two stories that we demonstrated recently. And the first story is to achieve so-called the single crystal thin solenoid fibers. So here, and we use this type of preform to fiber fabrication technology. And for example, in the core, and we put thin solenoid. The reason that we choose thin solenoid is simply because a thin solenoid is a star material for the thermoelectric applications, and especially for the single crystal thin solenoid, and it's fundamentally challenging to make it a single crystal, and it's even more challenging and to make that into different types of devices. So in order to show the feasibility of our technology, and we choose this semiconductor, which is rather challenging to make that into the single crystal. So after the thermal drawing, and because after we fabricate those fibers, because of the cooling effect from the surrounding, and we end up with a semiconductor core, but with the glass cladding. But if we look at the crystal structure of this semiconductor core, is polycrystalline. Simply because when we cool it down, and the surface, the temperature gradient that from the surrounding to the core, and so we cannot have a fixed crystal orientation. And if we cannot get the single crystal, and the device performance will be compromised. So we developed this technology, so-called the laser recrystallization. So we used a CO2 laser here, and to further process the material, and we gave this kind of so-called the directional heating and cooling. In this case, and we can use the laser to guide the crystal growth inside of the fiber. So after the process, and we will be able to achieve a single crystal thin solenoid. And after the fabrication, and we used XRD to map the length of the fiber, and we will be able to see this a single peak and along the entire length of the fiber to indicate the single crystal nature. And we also measure the thermoelectric performance between the single crystal and the polycrystal. And the polycrystalline is the one right after the thermal drawing, while the single crystal is after the post-processing. And here, and we can see the significant difference or the significant improvement. And when we change the crystal structure from the polycrystalline to the single crystalline. And further, to use those fibers for the wearable electronics, and we construct those thin solenoid textiles here, and we wave those fibers into a piece of a textile and use it to harvest the temperature, the thermal difference between the environment and also the skin. So this is the first story. And another part, when we consider the inorganic semiconductor, and by nature, and we want to form like different structures, fundamental structures. And the most basic structure when we use the inorganic semiconductor is so-called the PN junction. So the second story, I will show you how we use different tools and to achieve the PN junction inside the fiber. So here, this is so-called the thermocapillary convection. And similarly, and we use this semiconductor core here. And after the fabrication, and we see the core section of the fiber. Right in the center, we have the semiconductor core surrounded by the cladding. Now, firstly, we use the laser and to trigger this so-called capillary instability. And this capillary instability will transfer this continuous core into a chain of semiconductor spheres. Now, after we got those spheres, and we will continuously heat up this session, we want to induce this kind of a localized surface tension gradient. And when we have the surface tension gradient, and when we have this sphere under this laser heating region, and due to the surface tension, and the laser sphere will move to the direction towards the laser heating. So simply by adjusting the direction of the laser heating, we will be able to manipulate the position of those single semiconductor spheres inside of the fiber. So as a demonstration here, and we show when we have those 3 semiconductor spheres inside the fiber, and simply by heating the center one, and because of the thermal induced surface tension gradient, and only the center one starts to move upward. So this is also considered as a type of Marangoni effect here. And how we can use this one to assemble the in-fiber junctions. So basically, if we have like 2 cores, one is the P-type semiconductor, while the other one is N-type semiconductor. And firstly, we use the capillary instability to transfer that into the spheres. One is P sphere, while the other one is N sphere. Then we use the laser heating here and to drive those 2 spheres and gradually to move together, and eventually, and they will physically contact. So when they physically contact, and they will form this kind of a semiconductor PN junction. So this is the second story and about our effort and to form like a semiconductor inside the metal. And to summarize this effort, and last year, and we published this review paper, and to discuss about the semiconductor core fibers, and we systematically summarized the available technologies, for example, from the thermal drawing, as well as the post-draw processing, and for example, the one that I mentioned using the laser to do the processing. So if you want to know more details about it, and here is the paper information. So this is about the first session, how we incorporate those brittle materials into the fiber. And then the second session is about the soft materials. And for the soft material, to be more specific, and our target is the elastomer. And for the elastomer, actually, this picture shows here, and for example, this ball is made by the elastomer. And when you squeeze it, and it can be extremely deformed. And if you release it, and it will go back to the original state. And this is a very attractive property, and we can use that for the wearable electronics. However, when we use this one, and when we try to thermally draw this material into the fiber, and we encountered a lot of problems. The major reason is that the viscosity of this material, when we heat it up, and the viscosity drops a lot. So when we heat it up, it becomes liquid, and but when it's liquid, it's really liquid, like a water liquid. So in this case, and we will not be able to control it, and so we cannot form like any structure out of it. So our contribution in this field, basically, we try to fundamentally address this challenging. And here I would also like to share like 2 small stories. And the first story is that how we can successfully draw those elastomers. So the SEBS, this is a type of elastomer, and we cannot draw it directly. So what we did was that For example, we use this PVA, and we use a PVA here, and we structure the PVA. And we use a PVA as the part that can be used to hold the stress during the thermal drawing. So we use the PVA to design the structure, and on the outer surface of the PVA, and we use the SEBS to cover it. So during the drawing process, the stress is mainly applied to the PVA. So, and for the SEBS, it's just the naturally flow along the surface of the fiber. And eventually, and we demonstrated, for example, and when we change the shape of the PVA, and we will be able to fabricate those fibers. The beauty of the PVA is that after the fabrication process, simply by placing those fibers into the water, and the PVA will disappear. So, and we end up with like a single material SEBS fibers. So this is the fabrication part. After fabrication, and we infiltrate the liquid metals into those cores. And we have demonstrated, for example, when we stretch those fibers and over 19 times, and it's still electric conductive. And more interestingly, and when we test the mechanical property of those materials, and for example, here we have a piece of a fiber, and we drop a 1.5 kg weight, and this fiber was extremely stretched, but the performance was also maintained. And furthermore, and we had the user and to put the whole body weight on top of it, and repeatedly and to step on it and release, and still it gets the continuous readout from this type of material. And thanks to those high performance, and we try to use them for different applications, especially try to engage this type of like a sports monitoring. Because during the sport, and we see a lot of like a sudden impact, physical impact. And if we have the conventional like a wearable devices, they're quite easy to be damaged. So when we have those ultra stretchable fibers, and then for example, attached on the surface of the baseball glove, and even after this type of catching process, the high-speed catching, and we still those sensors still survive, and more importantly, they can also monitor, for example, the speed from different points, and which can help with the practice. So this is the first short story about how we use those soft materials. The second one is that we try to enable the functionality of the outer surface of the fibers. So if you look at like all the demonstrated works that we got so far, and they all focus on the center part of the fiber, which is so-called the core of the fiber. Then when we look at the outer surface of the fiber, which is so-called the cladding region, and the only functionality of the cladding is to provide the support and also to protect the core. So we try to come up with like a different method so we can use the cladding. This is our recent effort in this field. So what we did is that during the thermal drawing process, we try to have those so-called the patterned rollers. So when the fiber is out of the furnace and the fiber is still soft, so we mentioned this is the transition from the solid to liquid and liquid to solid. So it's still soft, and in that case, and we use those patterned roller and to transfer the patterns from the roller on the outer surface of the fibers. So basically during the drawing process, and because this is a continuous fabrication, and we will be able to cover the entire surface of the fiber with those micro scale and also nano scale patterns. So here, for example, we demonstrated that we will be able to print those two-dimensional dots on the surface. And if we shine the light and we see this beautiful diffraction pattern to indicate the high quality of those surface structures. Then further, we demonstrate, for example, we can also imprint those one-dimensional groups along the fiber perpendicular to the fiber or along a certain angle to the fiber axis. We'll be able to print those two-dimensional and with different heights on also outer surface of fiber. And here is more interesting that we can even print like very complicated patterns, for example, like the NTU 3 letters all over the surface of the fiber. And this process is continuous. And here shows that we can enable those three, for example, this spool of fiber shows the length is about 300 meters. And here that's the zoom in photo of this one. And you see those beautiful color patterns to indicate actually the surface of those 300-meter fiber is fully covered with those nanostructures. Then to use them for the wearable applications, we evolve them into the fabric and to make them into the self-powered sensing. And here we have the 3x4 fibers, and they form those 12 detection points, and to measure the pressure here. Here's one more thing, and I think like one speaker mentioned in the very early morning, and for the wearable electronics, actually, if we only look at the sensing part, it's pretty mature. But constantly we receive like a lot of information about, for example, how we should power those electronic devices. So since 2017, and we have started to develop like fiber-shaped batteries, and there are a lot of successful groups doing very attractive works regarding the fiber-shaped batteries. And here, this is our contribution here, and we try to focus on the Aqueous fiber battery, the rechargeable battery. And for example, here this photo shows for those black lines. Here you see those are the fiber battery, and they are very flexible, and they can also be knitted into the textile and to power the electronic devices. For example, like this LED continuous powering. And by far, we have demonstrated, for example, the zinc, sodium, aluminum, magnesium, and also potassium ion batteries. And well, more works will come out for this field. And the second part is that, for example, when we use those materials for the fiber battery, and actually we rely on the so-called the metal organic frameworks, the MOF, and they are the key, and that we can significantly improve the performance of the battery. So just a few weeks ago, and we published this paper and this review paper to systematically summarize the freestanding MOF electrodes, and especially for their applications in wearable electronics. And if you want to know more details about it, and please here is the details of the paper. Then by the end, I want to make a summary about what we have done for this thermal drawn multifunctional fibers. We have achieved like different types of sensing, and to make them to be the photo detection, acoustic detection, the pressure detection, the chemical detection, the thermal radiation. We also demonstrated within this beautiful platform that regarding the power generation out of storage. And on a separate note, actually, we are also currently working on to achieve the so-called logic gate in those fibers. So eventually, we will give this kind of the computing capability to the fibers. And by the end, I would like to thank all my present and also past group members. And without their hard work, and we will not be able to achieve so many interesting results. And I would also like to thank the support from NTU and the constant funding support from MOE, NRF, and also A*. And here's my email address and also my group website. So if you have any question, please feel free to drop me a message. Okay, thank you.
Thank you, Professor Wei. And I have a question about what do you think is the driving mechanism to make the thermally drawn fibers so superior elasticity? Like even for single crystal fibers that you were able to make that can be woven into fabrics.
Sorry, it's not very clear here. So please repeat the question. Thank you.
Yeah, so I'm wondering if you could share with us your insights in how these fibers can be so elastically deformed, even for the single crystal wires.
Oh, I think that's a very good question. Actually, that's also the difficulty that we are currently facing. So for example, for those single crystal fibers, and if you look at the cladding here, and the core indeed is single crystal. And actually, we have demonstrated that we can achieve single crystal like silicon germanium and tin selenide, and those are the ones. However, the cladding is always glass. And this is the part that's actually that cannot be fully compatible with the wearable platform and at least kind of a textile platform because of the usage of the glass. And one way that we are currently doing and to minimize this effect is always to give the coating. And during after the thermal drawing, and we gave this type of epoxy coating, and in this case, and that can protect the glass from cracking. But on a separate note, and this is only a temporary solution. So what we are doing now, and we have a work almost close to the end, and what we are doing now, basically, we developed a kind of fabrication technology, so-called the convergence method, and we will be able to extract the single crystal core here, and to make them be compatible with the polymer cladding. So when we change that into the polymer cladding, and because for those semiconductors, they are extremely thin, and even when you hold those semiconductor fibers, and you can easily bend them. And when we transfer that, for example, if we can change the cladding to the polymer, and they are very, very flexible. So this is the current efforts. And I think if we use the glass cladding, and unlikely it will be able to engage the real life application. And but currently, what we are doing now is to change the cladding to the polymer, and we have demonstrated like a very convincing results there. Yeah, thank you.